students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as stationary waves. Let's see an analytical treatment for stationary wave. Stationary waves. Now, let's consider a plane progressive wave. Let's consider a plane progressive wave with amplitude A, wavelength lambda, and velocity v, traveling in positive direction x-axis. Right? Now let's assume that y is the displacement at any point. The displacement y at any point is given by y is equal to a, we call that as say y1. y1 is equal to a sine 2 pi by lambda vt minus x. That's my general form equation of a progressive wave, right? Okay, now the equation of an identical progressive wave traveling along positive direction x-axis. Instead of that, if it travels along negative direction x-axis, the equation of an identical wave traveling in negative direction of x-axis. If the wave is traveling in negative direction of x-axis, then let's call that as say y2 is given by, I can say y2 is equal to a, since it is traveling in negative direction x-axis, this will be a sine 2 pi by lambda vt plus x. Now if this was minus x, this will be plus x. Now I can say by principle of superposition, if I use principle of superposition, the net displacement y is given by the net displacement y is given by y1 plus y2. So in that case I can say y is equal to a sine 2 pi by lambda vt minus x plus a sine 2 pi by lambda vt plus x. Here I can say that y is equal to a sine, I can take a common, a sine 2 pi by lambda vt minus x plus sine 2 pi by lambda vt minus x. Now sine plus sine, if I use factorization, is nothing but 2 sine cos. So in that case this is going to be y is equal to a 2 sine c plus d. So 2 pi by lambda vt minus x plus 2 pi by lambda vt plus x by 2 sine cos 2 pi by lambda vt plus x minus 2 pi by lambda vt minus x by 2. Right? Do we get this thing clear? Now once you have this, then I can say that y is equal to a 2 sine, I could take 2 pi by lambda common. So in that case, this is going to be Vt minus x plus Vt plus x by 2, and this is going to be cos 2 pi by lambda. I could take common, that's Vt plus x minus Vt plus x by 2. Here 2 and 2 gets cancelled, here 2 and 2 gets cancelled, minus x plus Vt minus Vt. So in that case, I'll get y is equal to a 2 sine. Now Vt plus Vt will give you 2 Vt. So this is going to be nothing but 2 pi Vt by lambda cos x plus x will give you 2x. So 2 pi x by lambda. Right? Now this can be written as, if I rearrange this, this can be written as y is equal to 2a. Let's write the cos term first. Cos 2 pi x by lambda sin 2 pi Vt by lambda. Now let us assume that let 2a cos 2 pi x by lambda be equal to, say, capital A. Let's assume that this term is capital A. So in which case I'll get y is equal to a sine 2 pi Vt by lambda. That is going to be my resultant of two waves, identical waves moving in opposite direction. Now this is the y is equal to a sine omega t. This is the general form equation of an SHM whose time period is the same as the two parent waves. So I can say that this equation shows the resultant motion shows that the resultant motion is SHM, right? This is your general form equation of SHM whose period is same as the two parent waves. Right? From this equation we also understand that the equation does not contain the term Vt plus minus x. That means I can say that hence it does not represent a progressive wave. Since the term x is not there in the equation, that means the displacement of the wave will have no effect on the resultant wave. The displacement of the wave will have no effect on the resultant wave as there is no x in this. Right? I can say also the equation does not contain the term Vt plus minus x. That means since the term x is not there, that means it is not a progressive wave. Hence it does not represent a progressive wave. Fine, do we get this thing clear? That means in the absence of term x, the resultant wave is not traveling either forward or in backward direction. Since there is no x, that means the resultant wave is going to be a stationary wave. If there was x, the wave would have either traveled in forward direction if there was a plus x, If there was a minus x, the wave would have traveled in backward direction. There is no plus x, there is no minus x. That means the wave is not traveling in either direction, right? I can say that in the absence of the term x, in the absence of the term x, the resultant wave is not traveling either in forward or backward direction. Hence, I can say that the resultant wave is a stationary wave. Hence, it is called as a stationary wave. It's not moving. There's no x term in it. Right? Now, let's try to think about the amplitude A. The amplitude A is a function of x. If you look at amplitude A, there's x in it. I can say that the amplitude A is a function of x, right? The amplitude A contains the term x, that is the position of the particle, and that is the position of the particle is different. For different particles you will have different position. Since the value of x is going to change, I can say that the position of the particle is different at different positions. So I can say that it's a function of x. Next, A we said is 2 cos pi x, 2 pi x by lambda. A is equal to 2 cos 2 pi x by lambda. Now I can say that the amplitude will be maximum to A, right? I can say that the amplitude is maximum when A is going to be equal to 2A, because we know that the maximum value of cos function is 1 and it decreases from 1. Now the amplitude is maximum when A is 2A for those values of x, for which the cos function, that's 2 pi x by lambda, is plus minus 1. If the value of the cos function is plus minus 1, that means the amplitude is going to be maximum, right? Now we know that cos of 0 is 1. That means I can say therefore 2 pi x by lambda should be equal to either 0 or it should be 180, 360 or so on. So at these values the amplitude is going to be maximum. Now there is a 2 here, so I can divide the whole equation by 2. If I divide the equation by 2, I can therefore say that x is equal to 0. Take lambda on the other side, 2 pi on the denominator, so lambda by 2. This is going to be lambda goes up, 2 pi gets cancelled, right, and so on. So the amplitude will be maximum when x is equal to 0, lambda by 2, lambda, and so on, right? That means the particle is going to therefore vibrate with a maximum amplitude. I can say that the particle situated at this point the particles situated at these points will vibrate with maximum amplitude. The particles situated at these points will vibrate with maximum amplitude, and that means there will be maximum displacement of these particles. That means I can say that the displacement is maximum relative to the other particle. The displacement of these particles is maximum relative to other particles, right? Such points are called as antinodes. Points where the displacement of the particles are maximum are called as antinodes, right? Such points are called antinodes. So these are those points where the displacement of the particle will be maximum. Okay. Now, in that case, from the equation, if x is equal to 0, lambda by 2, lambda 3 lambda by 2, I can therefore say that the distance between two consecutive antinodes is going to be lambda by 2. And say therefore the distance between two consecutive antinodes is going to be equal to lambda by 2. That will be the distance between two consecutive antinodes. Okay. Next, let's consider when the displacement of the particle is 0. Now I can say that the amplitude is minimum. The amplitude is minimum when A is equal to 0. Right? Now, when will A be equal to 0? For it will be equal to 0. Amplitude is minimum when A is equal to 0 for those values of x for which cos 2 pi x by lambda is equal to 0. Right? For these values of x, the value of amplitude will be 0. Now we know that. Yes, you want to ask me something? Right? Now, I can say that this is possible. Therefore, I can say that 2 pi x by lambda. We know that cos of 90 is 0. Right? Then 360 cos of 90. Then you can have 3 pi by 2 and so on, 5 pi by 2. Right? 90 is 0, 270 is 0 and so on and so forth. Now, in that case, I could therefore say that x is equal to lambda goes up and this is going to be nothing but 2 comes down, pi and pi gets cancelled. Therefore, I can say x is equal to lambda by 4. Lambda goes up, pi and pi gets cancelled. So this is going to be 3 lambda by 4, 5 lambda by 4 and so on. Right? Those are going to be the values of x. That means the particles situated at these points, lambda by 4, 3 lambda by 4, 5 lambda by 4, do not vibrate. Therefore, the particles situated at these points do not vibrate. Right? Since the particles situated at these points do not vibrate, the displacement of the particles at these points will always be 0. the displacement of particles at these points will always be zero. Such points are called as nodes. These points are called as nodes. Thus, a stationary wave is going to be made of nodes and antinodes. Now, if you look at this, the distance between two consecutive nodes is, if I subtract this is going to be nothing but lambda by 2. So the distance between two consecutive nodes is also going to be lambda by 2, right? That means from this expression, from this analytical treatment of stationary waves, we understand that stationary waves are made up of nodes and antinodes which are alternatively situated, and the distance between two consecutive nodes or two consecutive antinodes is lambda by 4. Therefore, I can say that a stationary wave is made up of nodes and antinodes. A stationary wave is made up of nodes and antinodes, and the distance between antinodes, the distance between nodes and antinodes, the distance between two consecutive nodes or antinodes is lambda by 2, right? Now once we have this, then I can have the diagram for this. That means a stationary wave is going to be made up of wave where you have maximum displacement and minimum displacement, right? Now you are going to have a wave that will be set up with maximum displacement and minimum displacement, maximum displacement and minimum displacement. Right? That's how you will have. This is going to be the point where you have minimum displacement, maximum displacement, minimum displacement. So this is going to be your node, antinode, node, antinode, right? So this is how your particles are going to be made up of. This is what your stationary wave is going to be made up of. Fine, do we get this in here? So I can say that when a transverse stationary wave is set up in a stretched string or wire, node are the points which are permanently at rest. There is going to be no displacement at nodes, and antinodes, right? Nodes are those points which are permanently at rest. In the case of a string, we can divide it into integral number of loops having equal number of lengths. So when you move a string in a waveform, you will have number of such loops that would be set up. Now I can say that each loop has a node, and at the end of which there is an antinode. Now the distance between two consecutive nodes is lambda by 4. Same way, the distance between two consecutive antinodes will also be equal to lambda by 4. Fine, do we get this thing here? So do we understand the analytical treatment of our stationary wave and how it looks like, right? Next. Let's consider a couple of more definitions here. What do we understand by displacement mode? Right? what do we understand by a displacement node? Now these are points where the particles of the medium has zero displacement, but the pressure and the density of the medium at these points varies between maximum and minimum value. Right? What are displacement nodes? These are points where the displacement, these are points of the particle where the displacement these are points of the particle of the medium having zero displacement, where the displacement is say 0. Right? The difference is, although they have zero displacement, the pressure at these points keeps varying. What is the difference? What is displacement node? The displacement of the particle will be 0, but in order to keep that displacement at 0, the pressure at that particular point will keep varying. The displacement of the particle does not change, but to keep that displacement same, the pressure at that point would vary. So I can say that, but the pressure and the density of the medium, at these points varies between maximum and minimum. Right? Now, so those are called as displacement nodes. Now, since the pressure at these points varies between maximum and minimum, so your displacement nodes are also referred to as pressure antinodes. Hence, I can say that displacement nodes are also referred to as pressure antinodes. Since there is a variation between maximum and minimum value of pressure, therefore they are called as, since it is varying between maximum and minimum value, therefore they are called as antinodes, and since it is only the pressure is changing, therefore they are called as pressure antinodes. Similarly, you can have displacement antinodes. Now, what are displacement antinodes? Like what I explained to you in displacement nodes, these are points where the amplitude is maximum and the particle varies between maximum and minimum value. Now, in order to make, if the particle is going to vary between maximum and minimum value, what should be the pressure at those points so that the particle can vary between maximum and minimum value? The pressure at those points should be minimum. Only if pressure is being exerted on a point, will the point be able to move? No. Only when the pressure is less will the point be able to move. So exactly the same thing happens. At displacement antinodes, the pressure is going to be minimum. Fine. So I can say that displacement antinodes, these are points where the amplitude is maximum and the displacement of the particle varies between maximum and minimum. Displacement of the particle varies between maximum and minimum. Right? Hence, I can say that in order to allow this, there's going to be no change in pressure and density of the medium at these points. It's all already going to be at minimum value. That's the reason why you have maximum displacement at these points. So I can say, but at these points, there is no change. At these points there is no change in pressure and density of the medium. Pressure and density of medium. Since the pressure and density of the medium does not change at these points are also referred to as pressure nodes. Hence, pressure nodes, the pressure does not change at these points, huh? So, right? Hence, displacement antinodes are also called as pressure nodes. Fine, do we get this in clear? Now, let's see what are the characteristics of a stationary wave. Now that we know that stationary waves are those waves which do not travel, have a maximum and minimum displacement. The maximum displacement is called as antinode. The minimum displacement is called as, that means when there is no displacement, that is called as nodes. Let's see let's summarize all of this. Let's summarize all of this into the characteristics of stationary wave. First, how is a stationary wave produced? A stationary wave is produced by superimposition of two exactly identical progressive waves traveling in opposite direction. That's how we got that. Remember, when we did analytical treatment, we said that y1 plus y2. And what was y1 and y2? These were two waves that were exactly identical and were moving in opposite direction. So, stationary waves are produced. I can say that stationary waves are produced. Stationary waves are produced due to superposition of two exactly identical progressive waves. Two exactly identical progressive waves traveling in opposite direction through the medium. In opposite direction through a medium. That's how they are produced. Now, since the two components of the wave have equal and opposite velocity, the resultant velocity of the stationary wave is zero. I have 2 points that are going to meet which are equal in amplitude and opposite in direction. Hence, the resultant velocity of the stationary wave is zero. Since the resultant velocity of the stationary wave is zero, hence the stationary waves are localized and there is no advancement of stationary waves. Fine, do we get this in clear? Since the two components of the wave, since the two components of the waves have equal and opposite velocities, therefore I can say that the resultant velocity of the stationary wave is zero. Resultant velocity of the stationary wave the resultant velocity of the stationary wave is 0, and hence a stationary wave is localized and there is no advancement of the wave in any direction. Hence a stationary wave is localized and there is no advancement and hence there is no advancement of the wave in any direction. Right? Next, if there is going to be no advancement of the wave in any direction, the two waves are equal, it is formed by two waves which are equal in magnitude and opposite in direction, therefore there is going to be no net flow of energy in any direction. The waves are localized, hence the energy is also going to be localized. So I can say that therefore there is no net flow of energy, there is no net flow of energy in any direction. Right? Now, when a stationary wave is set up in the medium, there are points which are permanently at rest, which are called as nodes, and the amplitude of variation as well as the velocity at these points are 0. So when a stationary wave is formed, you will have nodes and antinodes. There are going to be certain points that are going to be permanently at rest. There is going to be no displacement or there is going to be no velocity at these points. These points are referred to as nodes. There will be certain other points where the displacement and the velocity will be maximum, and those points will be referred to as antinodes. I can say that when stationary waves are set up in the medium, there are points that are permanently at rest. There are points that are permanent at rest. Those are permanently at rest and are known as nodes. The amplitude of vibration as well as the velocity at these points is 0. The amplitude of vibration as well as the velocities at these points is 0. Fine. Similarly, the points midway between nodes, two nodes, will have maximum amplitude of vibration, and these are called as antinodes. The velocity at antinodes is also maximum. So I can say that the point midway between nodes, the points midway between nodes will have maximum amplitude of vibration right, and these points are called as antinodes, and these points are called as antinodes. these points are called as antinodes. I can say that at antinodes, the velocity of at antinodes is maximum. Fine. Now the distance between two consecutive nodes or antinodes is going to be lambda by 2. The distance between two consecutive nodes or antinodes is lambda by 2. Right, that is going to be the distance. Now, nodes and antinodes are alternatively situated, and the distance between node and adjacent antinode is lambda by 4. Nodes and antinodes are alternatively situated and the distance between node and antinode is lambda by 4. Fine. So that's what is those are the characteristics of a stationary wave, right? In a stationary wave, all the particles except the node execute in SHM, and they execute in SHM with the same time period as the component waves. All particles of stationary waves except the nodes execute SHM of same time period as the component waves. Right? So, do we understand this? So, do we understand all the characteristics of a stationary wave? Right. We'll stop this here for the day. Thank you very much.